In this video lecture, we are going to see about the instruction sets of 8086 microprocessor. So more or less the instruction sets of 85 and 86 are same, but the representation of the registers would be different here. The extra instruction sets that are differ from 85s are string manipulation instructions, flag manipulation instructions, loop instructions, and then some of the unconditional jump instructions. Those are all the different instruction sets of 86 from 85. So we will see the instruction sets of 8086 microprocessor in this video lecture. Fine. So the types of instruction set in 8086 are data transfer instructions, arithmetic and logical instructions. Here we will perform addition, subtraction, multiplication, division, and then and or not logics. Then branch. So this is of unconditional and conditional branches. Then loop instructions, machine control instructions, flag manipulation instructions, shift and rotate instructions, string manipulation instructions. Okay, so these instructions would be new to you. String manipulation, flag manipulation, loop instructions. So these instructions are different for you or new to you. So in this, so all these, other than these three instruction sets, others are familiar to you as well. So first we will see data transfer instruction. Okay, so this data transfer instruction we will use for data transferring. So from the name itself, you would know that these kind of instructions are used for data transfer. If you want to move and data from one source, from one location to another location, you are supposed to use data transfer instructions. Fine. So the source instruction can be the source of data or operand would be like an immediate value. It might be an register or it might be an memory. Okay, so the destination also can be a register or memory. It can't be an immediate value. Fine. So the instruction will be like move destination comma source. Okay, the register or memory location where your operand is there is known as source. Where at what location you want to transfer this operand is known as the destination. Fine. So and this is your mnemonics move. So later in 8085 instruction set, if you want to move an immediate value to a register or memory, you will use a mnemonic called MVI, move immediate. So here in 86 you don't have such instruction. For moving an immediate value or for move a value from a register or memory location, we will use a common mnemonic called MOV. Fine. Okay. So you can perform register to register transfer, immediate to register, immediate to memory, register to memory, memory to register. Okay, these kind of transfers are possible. So we will see example for this. Okay, for moving from register to register, AX, BX. So move BX comma AX. So this instruction will move the operand or data from AX register to BX register. For example, before execution, if AX is having the value of 05, after the execution of this instruction, BX will have the value of 05 and AX will also have the value of 05. So why? In the sense, when you use data transfer instruction, the value is just copied and pasted. So it is not cut and paste, it just copy and paste the value from source to destination. Fine. So the next is register comma immediate value. Okay. So move CX comma 563A. So this is an hexadecimal immediate value which is of 16-bit. Fine. This is a 16-bit register. So you can move, you are supposed to move a 16-bit value into this register. So if we use an 8-bit register, you can use the value 8-bit value to move. Okay, fine. So the next is memory comma immediate value. If you want to move a value from immediate value to a memory, you can use this instruction. Because see to this example, This 5000 is also a 16-bit value, 563A also is 16-bit value, but the difference is that this is an operand and this is the memory location. Fine. So, to make a difference between the operand and the memory location, you are supposed to use the square bracket on the either sides of memory value. Fine. So, this is an example for memory comma immediate value. If you want to transfer a value from register to memory, you can give the memory location and then the register. Fine. So, here you are moving an 16-bit value. So, how this operation will happen is L value will be moved to 6500 and AH value will be moved to 6501. So, this AX register is 16-bit, no, this will be having a 16-bit value, okay. So, this location 6500 is capable of occupying only 8-bit. So, it takes 2 consecutive memory location to store the 16-bit value. So, and then the next is from memory to register. So, this instruction would be like 6500. So, here the 6500 will be moved to AL register and 6501 will be moved to AH. So, these are all the transfer that are possible using 8086. The only transfer which is not at all possible is memory to memory. You can't move a value from a memory location to another memory location. This is not at all possible. Okay. If you want to perform this kind of memory to memory transfer, you are supposed to use a DMA controller. Okay. So, this is a separate IC. About this we will see later. Okay. In unit 3 we will see about this DMA controller. Fine. The next instruction that we can see is push source. So, which means if you want to store a value into a stack, you are supposed to use push operation. Fine. If you want to perform any operation in the stack memory, you are supposed to use 2 instructions. One is push, another one is pop. So, if you want to store a value in the stack, you are supposed to use push instruction. If you want to take a value out from the stack, you are supposed to use pop instruction. Fine. So, if we push a value into the stack, it will look into the stack pointer to know where the pointer is pointing, okay, in which location the pointer is pointing. So, from that it will get the value. First, it will decrement from the pointer value, put on the higher byte value, then a value will be decremented, then a lower byte value will be stored in the stack, and then the operation is over. Okay. So, here we can see an example. Push, you are supposed to give the source. So, here I have taken push AX, which means that the value from the AX will be stored in the stack memory. So, for example, consider this would be your stack memory. Fine. So, if suppose as AX register is having the value of 6A3B, okay, and then the stack pointer value is 7635. Fine. So, if 7635 is here, okay. So, what will do is the stack pointer will be subtracted by 1, which means it is decremented by 1, and the location it will be pointing is, so initially stack pointer will be here. If you perform push, it will be decremented by 1 and it will point here. So, at this location your AH value will be stored. So, this is your AX value in this is AH and this is AL. 6A will be stored in 7634. Again a value will be decremented by 1. Okay. So, where AL value will be stored, AL value is 3B. So, as a total the stack pointer is decremented by 2 locations. So, this is what given here, SP minus 1, SP minus 2. So, when you perform push operation, the address locations will be decremented and the value will be stored accordingly. Fine. So, the next is pop instruction. So, pop, you have to give the destination register here, because in push you are giving value to the stack, in pop you are getting value from the stack. So, from the stack you have to give where your value should be stored. So, it can be a register or it can be a memory location. Okay, here also the same, the source can be in register or it can be in memory location. So here I have taken memory location as an example. Fine. So consider this is your stack, and your stack pointer is pointing to the address. We will say take the same address 7635 7636 7637. Okay, so in pop I have already told you the stack pointer will be incremented. Fine. So here you are supposed to store the value in the memory location 5000. So consider this as your memory. Okay, fine. Okay, so the value, if stack pointer is pointing to 7635, the value in 7635 will be stored in 5000. So you consider if this is having 3a 3266, so this 3a will be stored in 5000. Fine. So again the stack pointer will be incremented by 1, and from the value in that will be stored in 5001. So 32 will be stored here. Okay, then the stack pointer will be incremented by 1. So now the stack pointer value is updated to 7637. Okay, so first the value will be popped out from the stack pointer, it will be incremented, then the higher byte value will be taken, and then it will be incremented and it will be updated. The stack pointer will be updated to the another value. Fine. So here the final stack pointer value will be, yes, so first it will take from the location 7635. Okay, so this will be decremented, 7634 will take the value, the last is 7633. So the stack pointer value at the final is 7633. So here it is 7637. Here the stack pointer is incremented, here it is decremented. The next instruction is exchange instruction. Okay, so there in 85 we will able to perform exchange between only two register pairs, one is HL, another one is DE. But here you can perform the exchange operation between register and register, register and memory. Fine. So the format will be like exchange destination comma source. So the destination and source can be of a register or it can be of a memory. So here I have taken an example, exchange memory location comma register. How the exchange operation will happen is, so the lower byte and lower address, between the lower byte and lower address exchange will happen, and between higher address and then higher memory location the exchange will happen. So for example, if this is your memory, okay, so this is 5000, 5001, 5002, and you are having the value 5A62, and AX is having the value 6235. Okay, so how the exchange will happen now is 5000 will be exchanged with 35 and 5001 will be exchanged with 62. Okay, already the values, so okay, I will take an example 64. So after executing this instruction, the value will be like 5000 will have 35, 5001 will have 64, AX will have now 625A. Fine. So this is what will happen when we use this exchange instruction. The next instruction that we are going to see is in and out. So we will use this in and out when we are going to transfer a data between the input and output device and the processor. If you want to get a value from the input device, you are supposed to use in instruction. In that you are supposed to mention from which device you are going to get the value. So that device representation is given by its port address. So each and every device that we are connecting with the processor are through the pins. So that pin is having an address. So that address we used to call it as port address. Okay. So in instruction will be like you are supposed to give the accumulator register to which the value from the device will be stored, and then you have to mention the port address. Okay. So this value can give an 8-bit or 16-bit register. So in example I have taken 8-bit register in AL comma 08. So here 08 is nothing but the port address. Okay. So from the port address 80, the processor will receive the value and stores it in accumulator register. So this is for in, and the next instruction is out. So it will be like if you want to send a value to an output device, for example to a display. So the display will be connected through a pin, and that pin will be having an address. Okay, so you are supposed to send and receive the value to the input and output device through only accumulator. So AX register is the only thing that you are supposed to use to receive and transfer the value to the input and output device. Okay, if you want to receive a value, the value from the port address will be stored in AX register. If you want to send a value to output device, the value to be transferred should be stored in the AX register. That's the concept here. Fine. So here the format will be like out the port address comma the register that you want to transfer. Okay, the value to be transferred will be stored in AL or AX, either it can be 8-bit or 16-bit, and then you have to mention the port address to which you have to send the value. Okay, so this port address you can mention in two ways. So one thing, you can directly mention the port address, okay, as of in this example, fine, or else you can mention this port address in DX register. So indirectly you can mention. Okay, so for direct I have given this example, for indirect I have taken this. Okay, this DX will have the 16-bit port address. So the value from the AX register is given to the port address mentioned in DX register. That is of out instruction. Fine. So the next instruction is LEA destination register comma source. So what is this LEA? In the sense, load effective address. So effective address is nothing but we will frame an offset value, no, that is called as effective address. This source can be of a register or an immediate address value. Fine. So I have taken this an example LEA SA comma BX DA. So here we have mentioned a bracket, which means that the value in this registers are address. Okay. So how this instruction will work is, the effective address formed by these registers will be stored in source index. So that's the operation of this instruction. For example, BX is having the value 3000 and DI, if DI is having the value 5500. So after this, after adding this, you will get 8500. So this value will be stored in SI register. That's the purpose of load effective address. Fine. The next instruction is LDS destination register comma address, or LES destination register comma address. So what this instruction will do is, it will load the DS means data segment, ES means extra segment. So this will load the data or extra segment from the value mentioned by this address. Okay. So I have taken an example LDS BX comma 5000. What will happen is, the value in the 5000, okay, will be stored in AX, BX as well as from the DX. Okay, the format will be like this. Okay, so from the address location 5000, the consecutive locations are there and the values will be stored like this. Okay, after executing this instruction LDS BX comma source, the value in 5000 will be stored in BL, 5001 will be stored in BH, 5002 will be stored in data segment lower byte, and 5003 will be stored in data segment higher byte. So this is how, using this instruction, you load the data segment or extra segment. Fine. So if you want to use for extra segment, you can use LES BX comma 5000. Okay. The first two locations value will be stored in the register mentioned in the instruction, and next two consecutive locations value will be stored in the data or extra segment. Fine. The next instruction that we are going to see is LA HF. So what L represents? It is load. AH is accumulator, AX registers higher byte, and F for flag register. So what will happen is, load AH from flag register. Fine. So the flag register's lower byte value will be stored in AH register. So that is of LAHF. So this instruction will used for to know the status of the flag register. So the flag register's lower byte will be a carry, auxiliary carry, 0, overflow. All these bits are in the lower byte of flag register. If you want to know the status of those bits, you can transfer that lower byte value to an accumulator higher byte value. From that you can read the value from accumulator, you can know the status of these bits. Fine. So by knowing the bits of the lower byte of flag register, you can use it for further applications in your program. So this is offload, and next instruction is store AH to flag register. So the content of AH register will be stored in the lower byte of flag register. So this instruction is used to affect the flag register. If you want to change any of the bits of lower byte of flag register, you can use this instruction. Fine. So why we are using these kind of instruction, in the sense you can't directly read or write the value from the flag register. That's why you are using load and store instruction to know the values or to write the value into a flag register. So the next instruction is push flag. So the push, I have already told you, the push and pop operation we will use only in the stack memory. So if you want to store a value of the flag register into the stack memory, you can use this push and pop instruction. If you push the flag register into it, I have already told you, so it will push to the location, it will be decremented by 1. So the higher byte of flag register will be stored, okay, and the stack pointer will be decremented by another value, and then the higher byte will be stored. Fine. So if the flag register is having the value, it's a 16-bit register, no? So for example, it's having the value 563A and stack pointer value is 6535, okay. So after executing this instruction, the stack pointer will be decremented by 1. So 6534, from this the higher byte value 56 will be stored. Again it will be decremented by 1, lower byte value will be stored, okay. So now the stack pointer value will be 6533. So this is for push. And next is pop flag register. So here from the stack memory we will store the value into the flag register. So for example, the same example we will take 6535 is your stack pointer, okay. 6535 is having the value of 32, 6536 is having the value of 3A, 6537 is having the value of 52. So after executing this instruction, the flag register will have the value. So first the 6535 value will be stored in the lower byte 32, then the higher byte will be stored, that is 3A, and again the stack pointer will be incremented, and the stack pointer value now will be 6537. Fine. So these are all the data transfer instructions. So next we will see arithmetic and logical instructions, okay. So there in 85 we were able to perform only addition and subtraction. So for multiplication and division we have written a specific program. For multiplication you are supposed to perform repetitive addition. For division you have to perform repetitive subtraction. So but here in case of 86 you are having a separate instruction, you are having a separate mnemonic for multiplication and for division. Fine. Okay, so all those instructions will be same as that of 85. So addition you can perform addition with carry, subtraction with borrow. Now you can perform multiplication and division also. Fine. So here the only thing that is not at all possible is you cannot add the value from a memory with another value from another memory. Memory to memory operation is not at all possible here in 86 as of 85. So first we will see addition, destination, comma, source. So there in 85 one of your operands should be in accumulator and the result will be stored in accumulator. So here is not that case. The source and destination can be of any of the registers or memory location, and the value will be stored in the destination. So the destination can be of register or memory. Fine. So here the format is, you can add a register to register, register with immediate value, register with memory, that is possible here. So I will give an example, add ax, sorry, we will take this bx comma ax. So what will happen here is, it will add the value ax plus bx and the result will be stored in bx. So destination we have mentioned the bx register. So if it is an immediate value cx comma 326AH, the value from cx register is added with C26A and the value will be stored in cx register. Okay. So if you want to add a value from memory location and a register, that is also possible. Okay. So you can also add, the destination can be of a memory also. Okay. So you can add the immediate value with the memory location also, that is also possible. Okay. So the next is addition with the carry. Here you have performed only just addition, here addition with carry is possible. I will take this as an example, ADC bx comma ax, what will happen is ax plus bx plus carry, the value will be stored in bx register. So to know the carry, it will look into the flag register, see to whether the carry is set or not. If the carry bit is 1, 1 will be added with this addition, or else 0 will be added and the result will be stored in the accumulator. So all these kind of a format is also possible with addition with carry. Fine. So the next is subtraction destination comma source, then subtraction with borrow destination comma source. So these are common as addition, but there addition is performed, here subtraction is performed. So I will take an example, subtraction ax comma bx, in the sense what it will do is, it will subtract the source minus destination and the value will be stored in destination. So this will happen here. If you subtract with the borrow SBB ax comma bx, what will happen is bx minus ax minus carry and the value will be stored in ax register. So this is what will happen here while in subtraction. So as the format I have said before, for addition, addition can be performed with register, memory with register, memory with immediate value, register with immediate value. So those kind of format is also possible with subtraction and subtraction with borrow. Fine. So next we will see about increment and decrement instruction. So increment, if you want to increment a value from a register or memory location, you can use this instruction. Okay. So this will be incremented by 1. Okay. So if you have mentioned a value, a register, I have given an example here. If ax register value is 3233, after executing this instruction, ax will be incremented by 1 and the value will be stored again in the ax register. So now the value will be 3234. Okay. So the memory location also you can use it here. So the next is decrement. You can decrement a value of 1. Here it is added to a value of 1. You can decrement the value by 1. So the destination or source can be the memory location. So what will happen is, the value from the memory location 5000 will be decremented and it will be stored again in the same memory location. For example, if the value in the memory location is 326A. Okay. So after executing this instruction, this will be subtracted by 1 and the value will be 3259 and this will be stored in the memory location 5000. So here it is incremented by 1, here it is decremented by 1. So the value will be again stored in the address of memory location specified in the instruction. Fine. So the next arithmetic instruction is compare instruction. Okay. So compare destination comma source. So this instruction is used to compare the value between two registers or the register on the memory location. Fine. So this will compare and tell whether the value is greater than or less than the another value. Fine. How it is telling in the sense, for example, so you take this instruction, compare cx comma bx. So here cx is destination, source is bx here. Fine. The immediate value also you can use it as a source, the value from the register, value from the memory also you can use it as a source. Okay. What will happen here is the internal operation of compare is subtraction. Okay. So this instruction will subtract Cx from Bx, okay, and check to the carry and the 0 flag. If the destination is greater than the source, then carry won't set, okay, 0 flag also won't set, which means that if the carry is 0, 0 flag is 0 in the sense the destination is greater than the source, which means that Cx value is greater than Bx. If Cx value is less than Bx in the sense, while subtracting you will get an borrow here, and the 0 flag is also not set. So when looking into the carry, if it is 1, then it means that Cx is less than Bx. So if two values are equal, for example you have 5 here and you also have 5 here, when you subtract you will get the value 0, fine. So that time 0 flag will set, carry flag won't set. So when the 0 flag is 1 and carry is 0, which means that Cx, Bx values are equal. Okay. So this source you can use as an immediate value, okay, or you can mention it using a register or from the memory location. So by seeing to these two flags, carry and 0 flag, one can determine whether the destination is greater than, less than or equal to the source. The next instruction that we can see is AAA, which is nothing but ASIC adjust after addition. So after performing an addition, if you want to adjust your result to an ASIC number, you can use this instruction, fine. So how this instruction can be used, we will see it now. Okay. So after addition, if you mention this instruction, this will look into the lower byte of AL register, fine. So consider that your result has been stored in AX. So in that the lower byte is AL and the higher byte is AH. So in this, the lower bit of the AL register will have the bit number 0 to 7. So in this 0 to 3 is your lower bits. So what this instruction will do is it will check to the lower bits, check whether the given value is less than or equal to 9. Okay. If this is less than or equal to 9, the value in the bits 0 to 3 of AL will have no change. The value will remain the same. Okay. And the higher bytes of 4 to 7 will here. So this will become 0. Okay. Then the AH, the value of AH will become 0. So this is what will happen when the lower bits of AL is less than or equal to 9. The other case, if it is greater than 9, the lower bits of AL is greater than 9, what will happen is the value of lower byte value 0 to 3 bits will be added with the value 6. Okay. Then 4 to 7 bit will become 0 and AH will be incremented by 1. So this is what will happen. If you use this instruction, it will check to the lower bits of AL register. We will see to an example now. So consider that the AL value is 67. Okay. So here the lower bits of AL register is this one, 0 to 3 bit, no. So this 7. This 7 is less than or equal to 9. So at that time, if we use this AAA instruction, what will happen? The AL value will have no change, so that it will be 7, and then the higher bytes of AL will become 0. So now the 6 has become 0 now. Then the AH register will also become 0. So what value will be there in AX register? AH has become 0 now. Okay. Then AL register, the lower bits does not have any change, the higher bit has become 0. So now the AL value will be 07, as a whole AX value is 0007. Okay. We will take another case. Here the AL value is having 6A value. Here A is greater than 9. So what will happen now? AL value will be incremented by 6. So L value will be 1010, 6 is 0110. So the value will be, so L value here after adding 6 we got this value 0000. So in this example, So now what we have told, AL value, higher bits of AL value will become 0 now. So we have carry, so that will be stored in AL of higher bits. Now this has become 0. Okay, and AH value will be incremented by 1. So now the value will be like this. So as a whole, AX value will be 0, 1, 0, 0. Okay. So this instruction will be used after addition. It will check the lower bits of AL, less than 0, no change, and higher bits will become 0. If it is greater than 9, plus 6 will be added with the lower bits and AH will be incremented by 1, AL remains 0. The next instruction that we can see is ASIC adjust after subtraction. So the before instruction we have used after addition, here you are using after subtraction. Okay. The operation is same. The lower bytes of AL will be checked whether it is greater than or equal to, less than or equal to 9. Okay. If it is greater than, something will happen. If it is less than, something will happen. There, if it is greater than 9, we have added 6 and AH will be incremented by 1. So here what will happen is it will be decremented to 6 and AH will also decremented by 1. Okay. So that's the difference between addition and subtraction. Fine. So we will take the first case. If AL, lower bytes of AL is less than or equal to 9, so 0 to 3 does not have any change, as we have discussed before. AL has become 0, AH will also 0. So if it is greater than 9, lower bits of AL has greater than 9, the AL value will be subtracted by 6, 0 to 4 to 7 becomes 0, AH will be decremented by 1. So here also I have taken the same example, the lower bits 7 which is less than, so we will follow this case. AL will have the same value 7, higher bits have become 0, okay, AH now has also become 0. So as a total, AX value will be 0, 0, 0, 7. So now consider this case. Here A is greater than 9. So AL value, what will happen? So in AL 6 will be subtracted. Okay. So what will you get? So you will get 0, 1, 0, 0. So 0, 4 will be in AL. Okay. So AL 4 to 7 has become 0. Then AH will be decremented by 1. So for example, if AH is having the value 62, okay, if you subtract 1, this will become 61. So as a whole, AX will have the value 0, 4. So this is for ASIC adjust after subtraction. So the next instruction that we can see is AAM, ASIC adjust after multiplication. Fine. So before this ASIC adjust after multiplication, we are supposed to see multiplication and division instruction. Later we will see about AAM and AAD. So the next instruction is multiplication, multiply operand. So this operand can be of can be mentioned using a register or it can be from the memory. Fine. So in this multiplication and division operation, one of your operand should be in the accumulator. Fine. So after multiplication, okay, with the memory location or with the register, the value will be stored in accumulator. If your result is equal to or less than 16 bit, the result will be stored in accumulator. If it is greater than 16 bit, the higher bytes of the result will be stored in DX register and the lower bytes will be stored in AX register. Fine. So here I have taken an example mul BX. So what will happen is it will multiply the BX value with accumulator AH and the result will be stored in AX register. So because when you multiply an 8-bit with an 8-bit value, the result will be 16-bit value. Okay. So if you multiply with CX register, so what will happen? AX into CX register, the value will be of, this is a 16-bit and this is a 16-bit value. The result will be of 32-bit. Fine. So in 32-bit, the lower byte will be stored in AX register, higher bytes will be stored in DX register. As a total, this is of 32-bit. Fine. This is for multiplication instruction. For division also, one of the operands should be in the accumulator. Fine. If you divide a 16-bit by 8-bit value, okay, this 8-bit value is your operand here. So this you can mention it using a register or memory location. Okay, the result will be your remainder and quotient, right? So for multiplication, after multiplying you will get a result. For division, your result will be your quotient and remainder. Okay, so in case if you perform a division between 16-bit and 8-bit, the remainder will be stored in AH register and quotient will be stored in AL register. But in the case of 16-bit by 16-bit, okay, the result might be a 16-bit, okay, at that case your quotient will be stored in AX register and remainder will be stored in DX register. This is for the case 16-bit by 16-bit. So now we will see about AAM, ASIC adjust after multiplication. So after multiplication only you are supposed to use this instruction. So what this instruction will do is it will change the packed number into unpacked number. So what's unpacked number is? So 36 is an example for packed number. Unpacked is you are splitting this value. 0603 is an unpacked number. Fine. So I have taken how this packed number is converted to unpacked in the sense the AH will be given a value by dividing the AL by 10. Okay. The remainder of this division will be stored in AL register. So we will see an example here. AL is having the value of 04, 9 is stored in BL, multiply BL. What it will do? AL into BL and the result will be stored in AX register. So after performing this addition you will have 0036. So 4 into 9 is 36. This will be stored in AX register. So now what I have given here, AH is AL divided by 10. AL value is 36 now. So 36 divided by 10, the value will be stored in AH. So that value is, if you divide this, you will get a quotient of 03 and the remainder is 06. Okay. So this is the result after AAM. See here, this packed number 36 has been converted into unpacked 0306. So this is what will happen if you use AAM. This you have to use after multiplication. Fine. The next instruction is ASIC adjust before addition. So if you want to perform a division, before that itself you have to use this AAD. So what this instruction will do is it will convert unpacked number into packed number, which means that 0603 into 36. Okay. So how this will happen is the lower byte value is got by multiplying the higher byte into 10 plus the value in the lower byte. So higher byte will become 0 here. Okay. See here, move AX comma 0105. So the value of AX now is 0105. So if we perform this instruction after division, what will happen is, so how we got AL? AH into 10. So AH value 01 into 10. So with that you have to add the value 5. So as a 10 plus 5 you will get 15. So now 0105 has become 15 now. Okay, and AH value will become 0 here. So after doing this instruction, what will happen? 0015 will be stored in AX register. So now 0105 has become 0015. Unpacked number has become packed number here. Fine. So next we will see about the logical instructions. Fine. So the logical instructions are AND, OR, NOT, XOR. So these operations are logical operations. So this AND or NOT logical operations you can perform between the registers, register and memory, memory and register. Okay, with immediate value also you can perform, but memory to memory logical operation is not at all possible here. So we will see the instructions one by one. Okay, the first logical that we have taken is AND, destination comma source. This is the format for it. So the value in the source will be ANDed with the destination and the result will be stored in the destination. So here I have taken a format. First one is AND register comma register. So the example will be like AND CX comma BX. So the value between these two registers will be ANDed and the result will be stored in CX register. Okay, you all know the truth table of AND, no? So 00 it is 0, 01 0 1 0 0 1 1 1. Okay, with this logic the AND operation will be performed here. Fine. Each and every bit of these two registers will be ANDed. Okay, the example for memory and register is and 6500 comma BX. So after ANDing each and every bit of these two memory location and register, the result will be stored again in the memory location. So with the immediate value also it is possible, BX comma 6262. This is an example for this. And register comma memory. So here this is an memory location. Fine. And immediate value with the memory. Okay. Okay, this is all the format. So the each and every bit from the destination and source will be ANDed and the result will be stored in the destination. Fine. The next instruction is OR. The operation will be of like 0 0 0 0 1 is 1 1 0 1 1 1 is 1. Okay. The format will be the same. Here you will perform OR, register to register, memory and register, register and immediate value. But the only thing is there we have performed AND operation, here we will perform OR operation. Okay. So the next is XOR. So what XOR will do is 0 0, you will get, when you perform XOR between the same value you will get 0, right. So with the different value you will get 1. This is the truth table for XOR. Okay. So the same format, XOR, register comma register, XOR, memory comma register. So the same format is also here. Fine. But the operation performed is XOR operation. The format will be same as for AND and OR.